Welcome to the deep dive. We're jumping into a new piece of research today that you sent our way. It's a paper titled Self-Adapting Large Language Models, and it asks a pretty fundamental question about where AI is heading.
It really does.
Yeah.
Think about the large language models most people interact with today, the chatbots, the writing assistants. They are astonishingly capable after they've been trained on, vast amounts of data.
Right.
But here's the catch. Once that initial training is done, they are largely static. They don't easily or, persistently learn new information or adapt their core abilities based on new experiences or data they encounter later.
Right. It's like training them on the entire internet up to, say, 2023, but then if something huge happens in 2024 or a new field emerges, they can't truly incorporate that into their foundational knowledge. You can, put new facts into the prompt, sure, but that's temporary.
Exactly. That's just context window stuff.
So this paper is staring that limitation right in the face. Their big, exciting hypothesis is, what if an LLM could learn to adapt itself? Could it figure out how to generate its own training data or maybe its own instructions on how to update its internal parameters?
Yeah, brings to mind how a human learns, doesn't it?
Yeah.
When you're studying for an exam, you don't just passively reread the textbook pages.
No way.
You take notes, you summarize, you make flashcards, maybe you rewrite confusing concepts in your own words. You are actively restructuring and augmenting the source information in a way that specifically helps you learn it better. And the paper uses this analogy. Can an LLM learn to do something similar? Can it learn to take notes for itself to improve its own learning?
That's a powerful analogy. So our mission for this deep dive is to fully unpack this concept. We'll explore the framework they've developed called SEAL, understand the nuts and bolts of how it works, dive into what the researchers discovered when they put it to the test in a couple of key areas, acknowledge the challenges they ran into, and then look at the broader implications this research has for the future of AI, all strictly based on the source material you provided, of course.
Okay, let's unpack this then. At the heart of this work is the framework they call SEAL, which, as you said, stands for Self-Adapting Large Language Models.
Deal. Got it.
And the fundamental mechanism that enables this self-adaptation is the model's ability to generate what the researchers term self-edits.
Self-edits. Okay, that sounds like editing your own writing, maybe, but for an AI, what does that really mean in this context?
Well, a self-edit, as defined in the paper, is essentially a natural language instruction that the model produces itself.
Okay.
These aren't just random bits of text, though. They are generated with a purpose. They can specify things like how to restructure data from a new piece of information or suggest specific optimization parameters, like learning rates for updating its weights, or even indicate which auxiliary tools, like data augmentation techniques, should be used during the update.
So the model is generating commands or blueprints for its own learning process. Is that the idea?
Exactly. It's creating instructions. And the purpose of generating these self-edits is to drive persistent weight updates.
Persistent being the key word there.
Absolutely. This is done through supervised fine-tuning, or SFT, which is a pretty standard way to update a model's internal parameters based on specific data examples. Unlike just providing information in the input prompt, SFT aims for a lasting change in the model's capabilities.
All right, but how does the model learn which self-edits are any good? How does it know if the instruction it just generated actually helps it learn or maybe makes things worse?
That's where the reinforcement learning, or RL loop, comes into play. It's quite clever. If you look at the concept shown in Figure 1 in the paper, you can kind of see the cycle.
Okay.
Given some new information or a task, that's the input context. The model first generates a potential self-edit, a candidate instruction, if you will.
Right.
Then critically, the model is actually updated using this generated self-edit and the input data. This is what they call the inner loop update, typically using gradient descent in SFT.
So it tries out its own instruction.
Exactly. It tries it out on itself. After this update, the researchers evaluate how well the now updated model performs on a downstream task related to that new information.
And that performance score, that's the reward signal for the RL.
Precisely. That performance serves as the reward for the outer loop RL training. The model's policy, essentially its strategy for generating those self-edits, is then adjusted to maximize that reward.
I see.
So over many iterations, the model learns to generate self-edits that consistently lead to improved performance after the self-update. It's learning how to learn effectively from new data by generating the right instructions for itself.
Fascinating. It's not just learning the data, it's learning how to structure the data and its own update process for better learning.
That's it, exactly. They mentioned trying a few different standard RL methods like GRPO or PPO.
The usual suspects.
Yeah, but they found them a bit unstable for this specific setup. So they landed on using ResTem, which they describe as a simpler, maybe more stable approach based on filtered behavior cloning. You could think of it as sort of rejection sampling plus SFT.
Okay.
And the reward signal is usually pretty simple, like binary. 1 if the self-edit leads to improved performance, 0 otherwise.
Makes sense.
Oh, and for efficiency during that inner update loop, because you could be doing that a lot, they use low rank adapters, or lower I.
Right, lower I. That allows for lightweight fine-tuning without updating the entire model.
Right, exactly. Which is pretty central when you're doing these updates potentially many, many times within the RL process.
Efficiency is definitely key if this is happening iteratively. Okay, so once they built the SEAL framework, how did they actually, put it to the test? The paper focuses on 2 pretty distinct application areas.
Yes, they chose 2 domains designed to show different but complementary forms of adaptation. One was knowledge incorporation, and the other was few-shot learning. They really wanted to demonstrate SEAL's versatility.
Okay, let's start with knowledge incorporation. What was the specific goal there?
The goal was to see if the LLM could effectively and persistently integrate new factual information from a given passage into its internal knowledge. And the key part is, meaning it could recall that information later without the original passage text being present in the input context.
Ah, okay, so this directly addresses that static nature of models we talked about.
Exactly, making the new knowledge part of its permanent memory, so to speak.
How did they set up this experiment? I think figure 2 in the paper shows the setup.
Correct. The model is given a new passage, let's call the context C. It then generates the self-edit, SE. Now, in this particular application, the self-edit is actually synthetic data. Specifically, it's in the form of implications derived from the passage.
Implication.
Yeah, they prompted the model with something like list several implications derived from the content. So these implications could be inferences, logical consequences, or even just restatements phrased differently from the original text. Basically, we used to reprocess the information.
And this self-generated list of implications becomes the training data for the fine-tuning step.
Precisely. The model is fine-tuned using SFT on these self-generated implications, and sometimes they included the original passage text in the fine-tuning data too. Then comes the evaluation. They tested the updated model's ability to answer questions about the passage without the original text being available in the prompt.
Ah, the no context test.
Right. They used a no context variant of the squad data set for those evaluation questions.
And the reward for the RL training loop here was simply the accuracy on those no context questions.
Yes. That accuracy score was the reward. So this trains the model to generate implications that are most effective for assimilating the new knowledge so it can be recalled later without the source text. It's learning to generate the best study notes for itself, essentially.
Okay, now looking at the results in Table 2, this is where it gets really interesting and frankly a bit surprising, isn't it?
It really is quite striking. First off, they showed that just fine-tuning the model directly on the raw passage text alone yielded almost no improvement over the base model's ability to answer questions without context, like 33.5% accuracy versus 32.7% for the base.
Wow, okay. So just reading the text again during fine-tuning doesn't really embed it for later recall?
Not in this setup, no. It confirms that simply exposing the model to the raw text via SFT isn't enough for lasting recallable knowledge. Then, they tried training on the passage plus synthetic data generated by the base model itself before any RL training. That showed a modest improvement, up to 39.7%.
Better, but not amazing.
Right. Then, they used synthetic data generated by GPT 4.1, a much larger state-of-the-art model, to generate those implications, and they gave a more significant boost, up to 46.3%.
Okay, GPT 4.1 synthetic data is better. That makes sense. It's a powerful model. But then, here's the kicker, right? After RL training, SEAL, using its own self-generated synthetic data...
Get this. It achieved 47.0% accuracy.
Wait, so it actually slightly outperformed the synthetic data generated by GPT 4.1, even though the base model they used, Qwen 2.57b, is significantly smaller than GPT 4.1.
Right. That's the profound insight here. The RL training allowed SEAL to learn a policy for generating training data that was more effective for its own specific learning needs than a generic output from an even larger, more powerful model.
Wow.
It learned to generate higher utility training data for itself.
So it learned how to teach itself better than a sort of generic super teacher could teach it. That's genuinely surprising. Where do you think that happened?
Well, I think it points to the power of that RL loop, optimizing specifically for the downstream task after the self-update. The model isn't just generating plausible implications. It's learning to generate implications that, when it's fine-tuned on them, lead to better recall without the context.
It's tailored.
Exactly. The GPT 4.1 data is good, sure, but SEAL's learned policy is tailored to the specific model architecture it's running on and the specific goal of persistent knowledge integration for that model.
And they saw similar results in a continued pre-training setting too, right? With like 200 passages?
Yeah, SEAL still outperformed baselines there, including the GPT 4.1 synthetic data again. It was 43.8% for SEAL versus 39.4% for GPT 4.1 synthetic. And Figure 5 also gives a nice visual, kind of showing how the nature of the self-generated implications changes over the RL training iterations. They seem to become more detailed and effective.
Right.
Oh, and they also showed in Table 6 that even if you try different prompts to make the baseline synthetic data better, like asking for longer implications or generating Q&A pairs instead of implications, SEAL's RL training still consistently added a significant gain, like 6 to 11 percentage points, on top of those already improved baselines.
So the RL is really learning an effective policy for generation, not just relying on a good prompt.
Exactly. The learning isn't just about what to generate, but learning the best strategy for generating it, given the task.
Okay, so SEAL definitely helped with integrating new factual knowledge. What about the second application, the few-shot learning one? How did they apply SEAL there?
Right. The goal in the few-shot learning domain was different. It was about seeing if the model could learn to generalize to completely novel tasks after only seeing a very small number of examples.
Like maybe just one or two examples of a new type of problem.
Exactly. They evaluated this on a simplified subset of the ARC-AGI benchmark, which involves abstract reasoning tasks. So this is more about adapting how to approach a new problem type based on minimal exposure, rather than just memorizing facts.
And how is the self-edit different in this setting compared to generating those implications? Figure 3 shows this setup, I believe.
Yeah, it's quite different. Instead of generating natural language text as the training data, the self-edit in this domain is a specification of tools and their configurations for the adaptation process.
Specification of tools.
Yes, they defined a set of available tools. These included things like various data augmentation techniques, think rotations, flips, resizing applied to the few-shot examples, and also optimization parameters, like the learning rate to use, the number of training epochs, or even the specific strategy for calculating the loss function during fine-tuning.
So the self-edit is more like a configuration file, essentially. The model gets the few-shot examples for a new task and then generates something specifying, okay, for this kind of task, you should use this data augmentation, apply it this many times, and set the learning rate to this value when you fine-tune yourself.
That's exactly it. The self-edit is a structured output that dictates how the subsequent adaptation step will happen. This configuration is then used to apply LoRa-based fine-tuning to the model, using augmented versions of the few-shot examples based on the self-edit's instructions.
Okay, and then the adapted model is tested on a held-out test input for that same new task?
Correct.
And the reward, just getting the right answer on that test input.
Yep. Simple binary reward again. 1, if the adapted model produced the correct output for the test example, 0 otherwise.
Okay, looking at Table 1, the results here are pretty dramatic in a different way.
They really highlight the impact of SEAL's self-configuration ability, yeah. Just using standard in-context learning, or ICL, putting the few-shot examples in the prompt, but not actually adapting the model's weights, resulted in 0% success on these ARC-AGI subset tasks.
0. Wow, okay.
Yeah, these tasks are tough without adaptation. Then they tried something called test time training, or TTT, with some self-generated data augmentations, but without the prior RL training to select and configure the best tools. That still only got them to 20% success.
Still pretty low. But SEAL, after his RL training where it learned how to choose the right tools and configurations for adaptation based on those few-shot examples,
achieved a 72.5% adaptation success rate.
Whoa, okay. That's a huge leap from 20%.
It's a massive jump. This shows that SEAL learned to autonomously figure out how to best adapt itself to a novel task, given limited examples, just by intelligently configuring the adaptation pipeline.
That's impressive.
Now, the paper does show an Oracle TTT baseline, which achieved 100%. That used optimal human-crafted configurations.
So perfect tuning is still better.
Right. There's still a gap between what SEAL learned to do autonomously and perfect human tuning. But going from 20% to over 70% purely through learning to self-configure, that's incredibly significant.
Yeah, absolutely. So what does this all mean from the experimental perspective? SEAL successfully demonstrated that an LLM can learn to improve itself in two fundamentally different ways: by generating effective training data to incorporate new facts, and by learning how to configure its own adaptation process to tackle new types of tasks.
Yes, it's a powerful demonstration of the potential for models to become active participants in their own learning. But, the paper is also very transparent about the challenges and limitations they encountered, which are important for us to consider too.
Right, no silver bullets yet. One they bring up is a classic issue in sequential learning: catastrophic forgetting.
Right. This is the problem where, as you update a model with new information, maybe learning task B after task A, there's a risk that it degrades or completely forgets the information it learned previously, task A in this case.
Yeah, learning new stuff pushes out the old stuff.
Kind of. They tested this by sequentially updating the model on new passages and then evaluating its performance on all the passages it had been trained on sequentially up to that point.
And Figure 6 illustrates this effect, doesn't it?
It does. It shows that performance on the earlier tasks gradually declines as more self-edits related to newer passages are applied. So SEAL, in its current form, is definitely susceptible to this forgetting.
But it wasn't like an immediate total collapse.
No, it wasn't immediate collapse, which is maybe somewhat encouraging. It suggests potential for improvement, but it indicates it's a real challenge if you want to use this approach for continuous lifelong learning. They suggest future work could explore methods like reward shaping to maybe penalize forgetting during the RL training, or integrating known continual learning strategies designed specifically to mitigate this problem.
Okay, that makes sense. Another limitation they mention is the computational cost.
Yes, that RL outer loop is quite computationally intensive. Remember, for each candidate self-edit the model generates during the RL training phase, they have to perform the full inner loop, fine-tuning the model based on that specific self-edit, and then evaluate the updated model's performance to get the reward signal.
That sounds slow.
They note that each one of these self-edit evaluation steps takes about 30 to 45 seconds in their setup. And you need many, many iterations for the RL policy to converge, so that time really adds up substantially.
Right, so scaling this up needs some thought. And finally, the current evaluation setup needs explicit downstream tasks or question-answer pairs to calculate that performance-based reward, doesn't it?
Correct. The current framework relies on having a clear signal of success or failure linked to the specific input data and the self-edit that was tried. This dependency on explicit evaluation criteria kind of limits training the SEAL framework on large quantities of just unlabeled data where you don't have those criteria readily available.
But they had an idea for that too.
They did. The proposed solution here, interestingly, loops back to the core idea.
Yeah.
The model could potentially learn to generate its own evaluation questions or test cases for the new information as it processes it.
So it generates the study notes and the practice quiz.
Something like that. This would allow for a kind of self-supervised RL training of the self-editing policy, potentially enabling it to learn from much broader, unlabeled data sources.
That's a neat idea. Okay, so connecting all these findings and challenges back to the bigger picture, what are the implications of this research for the future direction of AI? The paper's discussion section really goes there, and it's quite thought-provoking.
Yeah, what's fascinating here is how this work connects directly to some very real concerns about the future of large language models. The paper references projections suggesting that by around 2028, maybe even sooner, cutting-edge LLMs might have been trained on essentially all the publicly available high-quality human-generated text data out there.
You mean we might literally run out of novel text data to train them on? People talk about an impending data wall?
Precisely. If we hit that wall, or even just a significant slowdown in new high-quality data, how do we keep making models better? SEAL offers a potential answer. It provides a mechanism for models to generate their own high-utility training data. So when external data becomes scarce, the model could learn to produce fresh, diverse corpora for continued training or adaptation itself.
So the model shifts from being purely a consumer of human knowledge to becoming a producer of knowledge, or training material for itself.
Exactly. Imagine an LLM reading a complex new scientific paper. Using a SEAL-like mechanism, it could generate large amounts of, say, distilled explanations, hypothetical scenarios based on the paper, or question-answer pairs related to that paper, all for its own use.
using its existing knowledge to process and refine the new stuff.
Right. It essentially generates a personalized, high-density training set to update itself. This could enable continuous self-improvement and deeper understanding, even of really niche topics where external human-generated data is limited.
This seems incredibly relevant to recent work on models that use reasoning processes like chain-of-thought prompting.
Absolutely. There's a strong potential synergy there. Reasoning methods often involve the model producing intermediate steps or thoughts. SEAL could complement this by allowing the model to learn when and how to distill the insights gained during a complex reasoning process into its actual weights.
So it could update itself mid-reasoning, almost. Or maybe right after solving a hard problem.
Potentially, yes. To internalize the lesson learned and improve its future performance on similar problems.
And for agentic systems, models designed to interact with the world over time and learn from experience, this feels crucial.
It really is. For AI agents operating in dynamic environments, incremental knowledge acquisition and retention are basically non-negotiable. SEAL provides a potential mechanism for structured self-modification based on experience.
How so?
Well, after an interaction or observing some new situation, the agent could synthesize a self-edit that triggers a targeted weight update. This would allow it to adapt its behavior and knowledge over time based on its lived experience, if you will, rather than needing constant human retraining or relying solely on the limited context window.
So the overarching implication from this deep dive into the SEAL paper is that large language models might not be destined to remain these static artifacts, just defined by their initial massive training data set.
Correct. SEAL demonstrates a promising path towards language models capable of self-directed adaptation, continuous self-learning, and potentially scaling their capabilities, even if external data becomes a bottleneck. They can learn how to become more effective learners of new information over time.
Okay, so we've taken a deep dive into the SEAL framework today, exploring how large language models could potentially learn to generate their own training data and update instructions to self-adapt. We saw how this approach led to some pretty significant improvements in incorporating new knowledge and tackling new tasks from just a few examples.
Yeah, and in some cases, even outperforming synthetic data generated by much larger state-of-the-art models, which was really the eye-opening result for me.
Definitely. We also discussed the hurdles like catastrophic forgetting and the, not insignificant computational cost.
Right, and how the researchers are thinking about overcoming them, including that interesting idea of the model generating its own evaluation criteria.
Yeah. This paper really does present a compelling vision for the future of AI. If language models can genuinely learn to teach themselves how to learn more effectively from new information, what does that imply for the ultimate limits of their capabilities and their future rate of progress?
It certainly makes you wonder, what new types of AI systems, maybe ones that can evolve and improve autonomously over extended periods, might this kind of approach eventually make possible?
It definitely leaves you with a lot to think about.